Hello children, our next chapter is 13, Limits and Derivatives. This chapter is an introduction to calculus, which is mainly deals with the study of change in the value of a function as the points in the domain change. We give an intuitive idea of derivative. Physical experiments have confirmed that the body dropped from a tall cliff covers a distance of 4.9 t square meter in t seconds. That is, distance s in meters covered by the body as a function of time t in seconds, which is given by s equal to 4.9 t square. This table gives the distance traveled in meters at various intervals of time in seconds of a body dropped from a tall cliff. The objective is to find the velocity of the body at time equal to 2 seconds from this data. The problem is to find the average velocity for various intervals of time ends at t equal to 2 seconds. So velocity at t equal to 2 seconds, average velocity between t equal to t1 and t equal to t2, equal distance traveled between t equal to t1 and t equal to t2 seconds, which is divided by t2 minus t1. Hence the average velocity in the first t seconds, which is given by distance traveled between t2 equal to 2 and t1 equal to 0 by time interval t2 minus t1. At t equal to 2, we have 19.6. So 19.6 minus t equal to 0, we have 0 by 2 minus 0. So we get 9.8 meter per second. Similarly, the average velocity between t equal to 1 and 2. We get 19.6 minus 4.9. At t equal to 2, we have 19.6. At t equal to 1, we have 4.9 by 2 minus 1, which is equal to 14.7 meter per second. We compute the average velocity between t equal to t1 and t equal to 2 for various t1. So this gives the average velocity t equal to t1 and t equal to 2 seconds. From this table, we observe that the average velocity is gradually increasing. As we make the time intervals ends at t equal to 2, which is smaller, we get a better idea of the velocity at t equal to 2 seconds. Between 1.99 seconds and 2 seconds, we conclude that the average velocity at t equal to 2 seconds is just above 19.551 meter per second. That is, the value between 1.99 seconds and 2 seconds, the average velocity at t equal to 2 seconds, which is just above 19.551 meter per second. Now compute the average velocities for various time intervals starting at t equal to 2 seconds. As before, the average velocity between t equal to 2 seconds and t equal to t2 seconds, which is given by distance traveled between 2 seconds and t2 seconds by t2 minus 2. That is distance traveled in t2 seconds minus distance traveled in 2 seconds, which is distance traveled in t2 seconds minus 19.6 by t2 minus 2. So this table gives the average velocity in meter per second between t equal to 2 seconds and t2 seconds. In the first set of table, we have done to find the average velocities and increasing time intervals ending at t equal to 2. In the second table, we have found that the average velocity is decreasing in time intervals ending at t equal to 2. So we can conclude that the velocity of the body at t equal to 2, which is between 19.551 meter per second and 19.649 meter per second. Here at t equal to 2, it is between 19.551 and 19.649 meter per second. We say that the instantaneous velocity at t equal to 2, which is between 19.551 meter per second and 19.649 meter per second. We know that velocity is the rate of change of displacement from the given data of distance covered at various time instant. We have estimated the rate of change of distance at a given instant of time. So there is a change in distance at a given instant of time. We say that as derivative of the distance function s equal to 4.9 t square at t equal to 2 is between 19.551 and 19.649. We can say that the rate of change of distance, which is the derivative of the distance function at t equal to 2, is between 19.551 and 19.649 meter per second. An alternate way of viewing this limiting process is by plotting the graph. This is a plot of distance s of the body from the top of the cliff versus the time elapsed. In the limit as the sequence of time intervals h1, h2 approaches 0 and the sequence of average velocities approaches the same limit as just the sequence of ratios. C1 B1 by AC1, C2 B2 by AC2, C3 B3 by AC3, etc. by C1 B1, which is equal to S1 minus S0, which is the distance travelled by the body at the time interval H1 equal to AC1, etc. So the velocity of a body at time equal to 2, which is equal to slope of the tangent of the curve s equal to 4.9 t square at t equal to 2. We conclude that the sequence approaches the slope of the tangent to the curve at a point A. So velocity of a body at time t equal to 2, which is equal to the slope of the tangent of the curve s equal to 4.9 t square at t equal to 2. We need to understand limiting process in greater clarity from the above fact. Consider the function f of x equal to x square. Observe that x takes values very close to the value of f of x, also moves towards the value 0. We say that limit x tends to 0, f of x, which is equal to 0. When x takes values like -4, -3, -2, etc. till 4, we get f of x equal to -16, 9, 4, etc. till 16. X takes values very close to the value of f of x and also moves towards 0. So we write a limit x tends to 0, f of x, which is equal to 0. We can read this as limit of f of x as x tends to 0, which equals to 0. The limit of f of x as x tends to 0 is to be thought of as the value of f of x should assume at x equal to 0. Assume x equal to 0, in which the limit of f of x, which is equal to 0 as x tends to 0. In general, as x tends to a, f of x tends to L, then L is called the limit of the function f of x, which is symbolically written as limit x tends to a, f of x, which is equal to L. Note that there are essentially two ways that x could approach a number, either from left or from right. That is, all the values of x near a could be less than a or it could be greater than a. This naturally leads to two limits, right hand limit we can write it as RHL, and left hand limit which is LHL. So right hand limit of a function is the value of f of x, which is dictated by the values of f of x where x tends to a from the right. Similarly, the left hand limit from the left of a. For example, consider the function f of x. F of x which is equal to 1 when x is less than or equal to 0. F of x equal to 2 when x is greater than 0. So from the graph, it's clear that the value of f at 0 is dictated by values of f of x with x is less than or equal to 0. If x is less than or equal to 0, we get f of x equal to 1, which is said to be the left hand limit of f of x at 0. So we denote this as left hand limit as x tends to 0 minus f of x equal to 1. To the left of 0, we have the function f of x which is equal to 1. So left hand limit x tends to 0 minus f of x equal to 1. Similarly, the value of f at 0 dictated by the values of f of x with x greater than 0, which equals to 2. That is, when x is greater than 0, the function f of x is 2. To the right of 0, the function f of x is 2. So we denote right hand limit as limit x tends to 0 plus f of x equal to 2. Here we have the function f of x which is 1 when x is less than 0. That is, to the left of 0, here it is 0. To the left of 0, the function f of x equal to 1. So left hand limit denoted by x tends to 0 minus f of x equal to 1. And it is given that x is greater than 0, f of x equal to 2. So to the right of 0, we have f of x equal to 2. So to the right of 0, which is x greater than 0, we denote it as right hand limit x tends to 0 plus f of x equal to 2. Here it's given that x is less than 0 or equal to 0. When x equal to 0, then f of x equal to 1. So to the left of 0, we have the function is 1, and to the right of 0, we have the function f of x equal to 2. Left hand limit denoted by x tends to 0 minus, and right hand limit denoted by limit x tends to 0 plus. In this case, the right hand, left hand limits are different. Here left hand limit is 1 and right hand limit is 2. And left hand limit and right hand limit are different, which is not equal. Hence we say that the limit of f of x as x tends to 0 does not exist, even though the function is defined at x equal to 0. Limit x tends to a minus f of x, which is the expected value of f at x equal to a, gives a value of f near x to the left of a, which is called the left hand limit of f at a. And limit x tends to a plus f of x, which is the expected value of f at x equal to a, gives the values of f near x to the right of a, and this is called the right hand limit of f of x at a. If the right hand limit and the left hand limit coincide, we call that common value as a limit of f of x at x equal to a. Then limit x tends to a, f of x exists if right hand limit which is equal to left hand limit. If right hand limit is not equal to left hand limit, then the limit f of x does not exist. The limiting process with respect to addition, subtraction, multiplication and division, as long as the limits and functions under consideration are well defined. So there is a theorem without proof. Let f and g be two functions such that both limit f of x and limit g of x exist. Then first one, limit of sum of two functions is sum of the limits of the functions. That is, limit x tends to a, f of x plus g of x, which is equal to limit x tends to a f of x plus limit x tends to a g of x. Second one, limit of difference of two functions is difference of the limits of the function. Limit of f of x minus g of x, which is equal to limit f of x minus limit g of x. Third one, limit of product of two functions, which is product of the limit of the function. Limit x tends to a, f of x g of x, which is equal to limit x tends to a f of x into limit x tends to a g of x. Fourth one, limit of quotient of two functions, which is quotient of the limits of the function wherever the denominator is non-zero. Limit x tends to a f of x by g of x, which is equal to limit x tends to a f of x by limit x tends to a g of x. In particular, as a special case of third subdivision, when g is a constant function such that g of x equal to lambda, for some real number lambda, we have limit x tends to a lambda of f of x, which is equal to lambda of limit x tends to a into f of x. We illustrate how to exploit this theorem to evaluate limit of special types of functions. So limits of polynomials and Ration function. A function f is said to be a polynomial function if f of x is zero function, or if f of x equal to a0 plus a1x plus a2x square, etc. an x power n, where a1x are real numbers such that an is not equal to 0 for some natural number n. We know that limit x tends to a, x, which is equal to a. Limit x tends to a x square, we can write it as limit x into limit x. Limit x is a, so a into a, which is a square. Similarly, limit x tends to a x cube equal to a cube, etc. Limit x tends to a x power n equal to a power n. Limit x tends to a f of x, which is equal to limit x tends to a0 plus a1x plus etc. an x power n. So sum of the functions is sum of the limits of the function. So limit x tends to a0 plus limit x tends to a1x etc. limit x tends to an x power n. So using the theorem, limit a0 equal to a0 plus a1 of limit x tends to a into x. So using lambda f into x, which is equal to lambda into limit of f of x, etc. a power n into limit x tends to a x power n, which is a0 plus a1 into a plus a2 into a square plus etc. an into a power n, which is nothing but f of a. Therefore, limit x tends to a f of x equal to f of a. Then a function is said to be a rational function if f of x equal to g of x by h of x, where g of x and h of x are polynomials such that h of x is not equal to 0. Then limit x tends to a f of x equal to limit g of x by h of x, which is equal to limit x tends to a g of x by limit x tends to a h of x, which is equal to g of a by h of a. Theorem 2, for any positive integer n, limit x tends to a x power n minus a power n, which is equal to na to the power of n minus 1. The expression in the above theorem for the limit is true even if n is any rational number and a is positive. x power n minus a power n, which is equal to x minus a into x power n minus 1 plus x power n minus 1 into a, etc. x a power n minus 1 plus a into n minus 1. So limit extends to a, x power n minus a power n by x minus a, which is equal to limit of the sum of the functions, which is equal to, using the theorem, limit of sum of two functions or more functions is sum of the limit of the functions. So I am writing this as sum of the limit of the functions, which is equal to then a power n minus 1 plus a into a power n minus 2 plus etc. a power n minus 2 into a plus a power n minus 1. So we get a power n minus 1 plus a power n minus 1 goes on till a power n minus 1, which is up to n terms, which is equal to na to the power of n minus 1. Therefore limit extends to a, x power n minus a power n by x minus a, which is equal to na to the power of n minus 1. Thank you, children.